The three charges shown are located at the vertices of an isosceles triangle. Calculate the electric potential at the midpoint of the base if each one of the charges at the corners has a magnitude of 8 nanocoulombs. All right, so we've got this picture, okay? Each of the charges has a magnitude of 8. The top charge is positive, the bottom two are negative. This is an isosceles triangle, so this is also 10 centimeters. Okay, so we've got the two legs that are congruent, and then we've got our base down here, and we are asked to find the electric potential at the midpoint of the bottom. So we're looking for the electric potential at the midpoint. All right, so let's go ahead and look at our electric potential equations. Well, the electric potential is equal to Coulomb's constant times the charge divided by the distance from the charge to the point where you're calculating the potential. So this is the equation that we can use. We've got three charges, so we're going to have to find the potential from the first charge, the potential from the second charge, the potential from the third charge, and then add those three together. So let's go ahead and find the potential from the first. So we've got Coulomb's constant, 8.99 times 10 to the 9th, times the charge, which is, for charge 1, negative 8 nanocoulombs, so that's times 10 to the negative 9th, divided by the distance. So now we need to look at this isosceles triangle. Well, it's an isosceles triangle, okay? And we're looking at the midpoint of the base. Well, midpoint means the point halfway between. So if the whole thing is 6, then each of these is 3 centimeters. Now, just like we needed to convert nanocoulombs to coulombs by making it 10 to the negative 9th, we need to convert centimeters to meters. So divide by 100, get 0.03. Go ahead, substitute this into our calculator, and we get that the potential is negative 2,397 and 33 hundredths volts. So we've got the first one done. Next, we need to find the potential from the second charge. Well, again, Coulomb's constant, 8.99 times 10 to the 9th, times the charge, negative 8 nanocoulombs, so times 10 to the negative 9th, divided by the distance, which is 3 centimeters again. Well, it's exactly the same for this one. Okay, the two charges at the base and the distances were the same, so we get the same potential. Then we need to find the potential for the third. So, again, Coulomb's constant, 8.99 times 10 to the 9th, times the charge. This time it's positive 8, so 8 times 10 to the negative 9th, because it's nanocoulombs, divided by the distance. And this distance is not given up here. 10 is the leg. It's not the distance. The distance is the shortest distance. I need to go straight down from here until I get to the midpoint. Maybe you remember from geometry that if you draw this, that it's going to cut it and create two right angles here. If not, when you do cut it, you know these sides are the same. Those ones were the same because it was the midpoint. This is congruent to itself, so we've got congruent triangles. These two angles make a linear pair, and they're the same, so they have to add up to 180 and they're the same. Well, that means they have to be 90. So if you look, what we've just done is we've created some right triangles. So let's look at this triangle, okay? We've got a right triangle here. And when we've got a right triangle, we can find a missing side if we know two of them using Pythagorean theorem. So a squared plus b squared equals c squared, where a and b are the legs. Well, one of the legs is right here. That's 3 centimeters, so 3 squared. Plus the other leg is what we don't know, so b squared, equals the hypotenuse squared, 10 squared. So I have 9 plus b squared equals 100. Subtract 9 from both sides. B squared equals 91. So b is equal to the square root of 91. We type that in our calculator, we get a 9 and about 54 hundredths centimeters. Now again, when we put it in the equation, we need it to be in meters, so we need to convert that, so it's going to be 0.0954. Type that into our calculator, and we get that it is 753 and 88 hundredths volts. And now we want to know the total here, so we're going to add these up. So we have negative 2,397 and 33 hundredths plus negative 2,397 and 33 hundredths plus 753 and 88 hundredths. So we get the total voltage to be negative. So we get the total potential to be negative 4,040 and 78 hundredths volts.